Awesome. Well, I think we can go ahead and get started. My name is Alicia Gavin. I am the Digital Outreach and Design Specialist here at RoboNation. We are very excited to start off our second session in our MathWorks mini-series, talking about estimating the direction of arrival with MATLAB. And here from MathWorks, we have Colonel D'Souza, and he's going to be speaking with us today. We'll have some questions at the end, and you are more than welcome to ask any questions then. So I'll pass it over to Connell. Thank you.
Awesome. Thank you, Alicia. I'm just going to go ahead and share my screen real quick. I think I got the right one. So I'm not sure what screen I'm sharing. Do you guys see MATLAB on the screen? Is that? Seem to have lost my, I don't know what I'm sharing. All right, cool. Simon says yes, so let's do this. All right, so today what we're going to talk about is, we're going to talk about estimating direction of arrival. It's a very common task that a lot of y'all taking part in RoboNation competitions have to do, especially on the marine competition side, so robotics, roboboat, robosub. Essentially, what you'll have to do is you'll have some kind of acoustic pinger or an acoustic beacon under the water that's pinging flashes of sound waves, if you will. Essentially, what you need to do from your robot is you deploy an array of hydrophones, and this array of hydrophones is going to try and identify which direction that ping is coming from, and then you have to, drive there and perform some action after that. So what we're going to talk about today is how in MATLAB you can essentially build simulation models to test direction of arrival estimation algorithms. We also have a few canned algorithms within the product, so you don't really need to go and reinvent the wheel. You can essentially just use one of our standard, and we've got implementations of a number of direction of arrival algorithms like the music and et cetera, et cetera. So we can go through that in a little bit. But I don't have any slides today. I'm just going to talk through this little example. I can send you a link to this example in the chat real quick if you give me 1 second. I have it up here somewhere. And we have examples on both. We have examples on using both a passive sonar system as well as an active sonar system. So what we're going to talk about here is just a passive sonar. Oops, I think I lost the page. But what we're going to talk about here is using a passive sonar array, but we've also got an example on how you could do something very similar with an active array as well. So I'm going to pop a link to this documentation example in the chat. You can open it up. If you have MATLAB, you should be able to open it up directly. If you don't, this example is part of the phased array toolbox, the phased array systems toolbox. Phased array system toolbox deals with different things like different phased array kind of applications, right? So radar, sonar, ultrasonic, et cetera, et cetera. But we offer a complimentary license to all RoboNation teams, and if you need access to this toolbox, this toolbox is on that license. So we can send you a link as to where you can get these licenses in a little bit. But yeah, you should have access to this toolbox, no problem. All right, so without wasting too much time, I'm going to jump right into this example. And as you can see, we've set up a very simplistic scenario here, right? This scenario is very similar to what you do at RoboNation. It's just using a sort of sanitized environment. So essentially, what we have here is we have this acoustic beacon that's 1 meter from the surface of the floor in this tank, and then you've got a boat that's towing a passive array, a 5-element uniform linear array of hydrophones, right? And again, this will be something very similar to what you do at one of the, if it's RoboSub, you probably have the hydrophone attached to the submarine because you're already underwater. But with RoboBoat or Robotics, you probably have a arm that deploys the hydrophone array into the water when you have to listen to these pings. Okay, so before we get started, the first thing that you have to do is you have to be able to design the array, right? That's a very crucial part of this challenge. And to do that, we've got an app called, let me just pull that up real quick so I get the name right. But the app is called the Sensor Array Analyzer app, which you can find in the Apps tab in your MATLAB window. So once we go ahead and click that and it launches, essentially what you see here is oops, I've got two of these open. So what you see now, what you see is this is the way for you to sort of try different permutations and combinations of hydrophone arrays, right? So you can you can start by going to the array tab, and you can pick either a uniform linear array, uniform rectangular array. These are all two-dimensional arrays. So a wide variety of what you can choose, but you can also choose three-dimensional arrays like a spherical array or a cylindrical or arbitrary. Arbitrary is something that if you want to build an array that's not one of the shapes that we've got up there, you can use this arbitrary array option to build that for you. So if I click on that real quick, and while this loads, you see this is it's just a 3-array unit, but it's kind of in like a triangle shape almost. But you can at the same time sort of give it z direction values as well, so you can actually have a volume rather than just a single two-dimensional array. But for the purpose of this, let's just go and take a look at the uniform uniform linear array and see what this app can help you with, right? So you've got the ability to add numbers of elements. So you can say, okay, I like we said in that example that we've got, we're using a 5-element array. You choose the spacing. You can either choose it as a function of the spacing in terms of meters as a unit, or in terms of your signal wavelength, right? And then you can pick the array. So you pick the axis. So is it vertical, horizontal, or in the z direction? Okay, so once you sort of build your array, the one thing that you want to see is what I also didn't talk about is you can also choose a bunch of your sensor elements, right? So in this case, what we're looking at is we're looking at hydrophones because that's our sensor element. But if you're working on if you're working with antennas, it's the same. There are a bunch of different sensor elements that you can try. So we're going to pick the hydrophone because that's what this problem needs from us. You can do things like replication or partitions. Again, these are these for people that are experts in this area, this makes a lot of sense to them. But the one thing that I really like about this is once I say, okay, I want a 5-element array and I hit apply, it'll essentially build that array for me here. But I can also take a look at the 3D pattern, for example, to see what the coverage of the sensor is. So if I can just resize all this a little bit, this is going to give you a nice plot that says, okay, this is what my array can do. This is what its field of view is, if you will. And then you can just as well go and play around with this number and say, okay, I want to do maybe 3 instead. Voltage sensitivity, adjust all these kind of parameters in here, and it'll update this on the fly. So a very handy app when you're starting off trying to design what your array should look like. But essentially, once you're happy with this and you're happy with what your array looks like, there are some more plotting options that you can take a look at. So you can take a look at the azimuth pattern in 2-dimensional in 2D, and so on and so forth. But it's essentially once you've figured out the array that you need and the array that works best for you, you can export this to MATLAB either as a MATLAB script or just as an array object, and we can take a look at that. So I'll just generate the MATLAB script real quick, so you can see what it looks like. And essentially, we're using this phased array system objects. Phase.ula. This is when you're actually setting up the array. Some more information on element spacing and array taper and so on and so forth, as well as any other sort of any of your sensor specs, right? So what is the voltage sensitivity? What is the propagation speed? This is typically, in our case, it's the speed of speed of sound in water, right? Which is a known value. But then also, what is the frequency that you're expecting to hear? So I believe at RoboNation competitions, it sort of lies within that 27 kilohertz to 40 kilohertz range. So you can sort of specify that, and then it's just got some plotting tools after that. So let's jump back to our example, and I'll show you what that looks like when you're actually building the array for the example purpose, right? So the first thing that we have to do is what we're doing is we're essentially setting up a simulation environment, right? So part of what we have to set up is we've got to set up the channel and the different multipath, because multipath is a big problem when you're trying to deal with acoustic, hearing sounds underwater, right? Acoustic beams, they sort of tend to bounce off the different surfaces that you have, whether it's the wall of the tank, the floor, the air water interface. Acoustic waves will bounce off that and create multipath issues for you. So you have to be able to deal with that, because if you're not filtering, if you're not getting that clean data that comes in, you're essentially getting a corrupted sound that's bouncing off somewhere. So it's not the sound wave that's coming right off the beacon. It's something that's coming. It's still sound waves coming off the beacon, but it's after it has bounced off one of the various surfaces in there. So essentially, what we're doing at the start is we're saying, okay, and this is so we're setting up some parameters initially. Propagation speed is 1520. This is the speed of sound underwater. It's a pretty standard value. Obviously, depending on what kind of water you're in, that would change, or what kind of fluid you're in, that would change. The second one is channel depth. So this is how deep the tank is. We've set it to 200 meters. You can change that to whatever. I know at RoboSub you have it used to be in the transdeck, so you can calculate what the depth of that is, and then feed that in here. The next one is the operating frequency. So this is the operating frequency is the frequency at which the frequency of the beacon. So as you can see, the acoustic beacon that we're modeling here transmits a 10 millisecond pulse at 37.5 kilohertz. So that's just what we're setting up here. The next thing that we have to do is we actually have to set up that multi-path channel. So the way we do that is we use the phase iso speed underwater paths function method of system object. And we're giving it parameters like the channel depth. We can set this number of paths source as a property. So if you set it as a property, you can actually give it a value. I believe the default value is 10. But if you can either choose to use the default value, or you have to declare this as a property, and then you can feed that in as an input to that. And then we're also talking about the propagation speed. So what is the medium, right? And then we pass this isopaths object into a multi-path channel system object, which is what actually creates the channel. If you so the first part of this demo is just defining what that underwater channel is. The next thing that we want to do is we want to define the beacon, so the acoustic beacon and the array, right? Because we're going to model what the beacon looks like. I believe y'all can reach out to RoboNation and ask them for specs on their on the beacon that they use for the competition, but you can just feed that information in here. So essentially we're saying, okay, this waveform that we're modeling here is a rectangular pulse, which has a 1 second repetition interval. So the PRF, which is the repetition interval, is 1. The pulse width is 10 milliseconds. Again, this is the information that you can talk to RoboNation and get about the beacon that they are using at the competitions. Then we calculate the pulse bandwidth, which is 1 over the pulse width, and also the sample rate, right? So 2 times the pulse bandwidth. These are all very common, very common computations. And now what we're doing is we're using this wave system object to create a rectangular waveform. So we give it the different parameters. We say, okay, it's got a 1 second repeating interval with a pulse width of so much, and so sample rate, right? So again, we've just gone ahead and defined this acoustic beacon. Let me actually go and run these sections as well, so we can see what happens in real time. And what you're seeing right now is a live script. So MATLAB live scripts are kind of cool. They they help you with. I call MATLAB live scripts cheating because, for example, if I do something real quick here, say if I start typing in, it's already going to tell me all the variables that I've got, all the variables that are further along in the sheet. It's able to identify them or give you hints on what a function would look like. So it's very nice because you don't have to remember function names, which is really hard sometimes because there's just so many functions available. But it's also it's smart enough to figure out, given whatever data you've got in your workspace or earlier up in this live script, it's able to identify which functions you think. It's smart enough to at least give you hints on which functions it thinks you are wanting to use next. Okay, so what we've done now is we've modeled the acoustic the waveform more than the beacon. We've modeled the waveform first, and then now we got to, based on that waveform, create the acoustic beacon, right? So when we're creating the acoustic beacon, we want to give it we want to give it the type of sensor that it is, where is it located, so on and so forth, right? So we're going to create a projector, right? So this projector is essentially saying, okay, this beacon is going to be projecting sound out, right? So that's what we call it. So we're creating an isotropic projector. Again, these are all just single line functions in MATLAB that are really easy to use. Now that we've created the projector, we want to create a projection radius. So the radiator is the piece of code that's saying, okay, these beams are going to be traveling out from that point in space. So we give it the projector with its voltage response. So it's got that element in there, but we're also giving it the propagation speed as well as its operating frequency. And this is, in this way, we're setting up that beacon in there. And then we have to create a platform for the beacon. So this is what tells you where in space the beacon is, right? So we say it is the beacon's, it's got an initial position of these values up there, and it's got an initial velocity as well. But we can actually, let's try and play around with this. Let's give this. We want to keep our beacon stationary. So I'm gonna change that to 0. And so now what we've done by running this section is we're able to define what our acoustic. We've sort of modeled our acoustic beacon, right? We've got just 3 functions, and you're able to do that real quick. The next thing that we're going to go into is the passive towed array. So this is the hydrophone array that's on your robot that's being driven with the this is what we're going to use to actually capture the sound and identify which direction it's coming from. Okay, so again, if you remember from that app, we're using a phased ULA, which is a uniform linear array. We're telling it what element it is. So we're telling that it's a hydrophone. We've got 5 sensors. For the element spacing, this is a very common formula used to identify element spacing in a hydrophone array. It's just the propagation speed divided by the 2 times the operating frequency, right? So I'm not a signal processing expert, but from whatever literature I've read, this is what they typically use to identify how far apart you want to space the different elements in your hydrophone array. Okay, so this is where we're defining it, the array. Now we've got to create the collector. So we pass the array into this phase.collector system object. And then lastly, we have to create the platform from there, right? So the platform will define where in space it is. So we're saying it's got an initial position. So it's 10 units in the Z direction under the water. So it could be, depending on what you define your units to be. And then what we're also going to say is that because this thing is stored, we're going to move this at 1 meter per second, right? So your robot's moving at 1 meter per second, and we're going to use this moving robot to sort of find which direction the sound is coming from. Okay. The last thing you want to do, and this is something that, again, this is a software preamp. If you're actually building a hydrophone system, you may have a physical hardware preamp on board that's getting that signal and just boosting it enough so you can capture good information from it. So, but essentially just saying, okay, just boost this by 10. We're giving it a little bit of noise as well. So because that's everything that we're creating here is going to be very sanitized information, right? It's clean software generated information. That's typically not how your actual hydrophone data is going to come in. Remember that you're going to have things like motors and other things that are creating sound on your robot. It could be the fan on your computer that's creating some vibrations under the water that will also add noise to your signal. So you have to figure out a way to deal with that, right? Because in simulation you can get a lot of clean data, but in the real world, that's where sort of simulation that's the difference between simulation and the real world is the amount of noise that's generated. So we're giving it a little bit of noise as well, and then essentially creating this preamp that's going to boost our signal a little bit once it comes in. So I'm going to go ahead and let me just run all of these sections real quick. I think I forgot to do that. But now what will happen is if we go into our workspace, we see all of these things created here. So we see the array platform. This is a system object. It's saying we're using a velocity motion model. It's got an initial position, and it's got some orientations as well. Similarly with the beacon platform, these are all system objects that are created, as well as the channel which you see here. So you can take a look at what's going on over there. But let's go back to the live script again. So what we're going to do now is we're going to run a simulation to just see what the data looks like, right? We don't know what it looks like. So let's go ahead and run this section. I'll tell you what's happening in here. But essentially what we're doing is we want to capture 10 pings. Okay, so 10 pings from the beacon. We're trying to just capture the information to see what it looks like. Ooh, unrecognized variable Rx. That's interesting. Oh, maybe I just didn't run this section. That's why. Oh, there we go. Okay. So again, wave x equals wave. This is that waveform that we created earlier. We're trying to find 10 pings, and we're just initializing this R, so Rx, so receiver signal. We're just initializing the receiver signal, so it's it just helps with memory allocation. So we put this in a for loop. Beacon platform. So beacon, this is the system object that we created earlier, the phased array. So this is the platform for the beacon, for the acoustic beacon, and then the next one is the array platform, which is the system object for the array. Now we know that the beacon is stationary. It's not moving, and essentially what we're doing by passing in this sort of so PRF is the it's a frequency at which the pulse is it's at 1 second. What do we call it up here? It's the repetition interval of the platform. So essentially what we're doing is we're saying, okay, at every 1 second, what is the position of the beacon and what is the position of the array? So we know that the beacon is going to remain in the same place, but the array is going to keep moving forward by 1 meter per second, right? So that's essentially what's, so with that, we're essentially trying to get what the position and what the velocity of these two platforms are. So we expect the beacon platform to have the same position and 0 velocity, whereas the array platform will move forward by 1 meter every second. So that's going to change, but at a constant velocity of 1 meter per second. Okay. Now what we need to do next is we need to compute. We essentially need to compute all the paths that the sound coming out of the beacon will use to get to the array, right? So there's this isopaths. Again, isopaths is that system object that we set up right at the start. We're feeding in the position of the transmitter, the position of the receiver, the velocity of the transmitter, the velocity of the receiver, and that repetition frequency, or the inverse of the repetition frequency. And what this is going to give us out of this is it's going to give us all the paths, right? So this is you can look this up in the documentation, but essentially this is a 3 by number of transmits frequency, or 3 by number of transmits array. Where the first one gives you the path, the second one, so 1 indicates that it is the direct path, -1 is the first bounce of it, and then so on and so forth. And then that last the last row is essentially giving you the Doppler velocity shift, because when things are moving, when there's relative motion between a transmitter and receiver, there is a Doppler effect that you have to take into account, right? So essentially this isopath is setting up these paths for us, right? Now we have to propagate that acoustic beam, the acoustic beacon waveform. We've got to propagate that through our channel. So T sig, which is the signal from the transmitter, we're going to get that because we've got this radiator. Again, there's something that we set up there, and we're going to give it X, which is the waveform, and source angle, which is one of the outputs that comes out of this isopath function. But what that is that's giving you the angle at which the wave is exiting the transmitter, right? And similarly, on the receiver side, we use the channel to make sure that, okay, so we're feeding that information into the channel object, and it's going to tell us based on all those multipaths that are there, what is the signal that the receiver is getting at the end, right? So the T signal, which is the one that we just computed earlier, we're going to give it that paths vector, or the paths matrix, which takes into account the Doppler effect and so on and so forth. I believe this is, I can look it up real quick. I don't remember off the top of my head, but I can come back to that real quick. It is the we could come back to that real quick. But again, these are values that come out of this come out of this isopaths channel, right? So we're feeding that into to build that the signal that our beacon is receiving on the end. And now we're going to collect this propagated signal into our array collector, which is another thing that we set up earlier. So we give it the R signal, so the signal that the receiver is getting, and then also the angle at which it's getting it at, right? Azimuth and elevation angles that it's getting it at. And now we're essentially storing the signal. So this is what one ping of the signal looks like. As you can see, it's sort of quiet, and then we get that ping from the beacon, and then it's this is just noise after that. So what we're doing here is we're only plotting one single element of this. But if I go ahead and plot all of them, you'll see that they're essentially a number of signals loaded one on top of each other. It's taking a second to run. While this runs, does anyone have any questions? You can pop them into the chat real quick while we wait for this to run. Oh, I heard something ping. Alrighty, I think I got MATLAB to hang, which is always fun. Okay, so that works. Well, for some reason, I don't know why it's not. Maybe it's because I'm sharing this like a graphics lag that's happening. But essentially, what will happen is if you plot all the signals, you'll see them just in different colors, overlaid one on top of the other. But this is what each individual ping looks like. It's just a peak that comes through, um, uh, and this is what our receiver is hearing, right? So we're plotting the RX signal. So I'm going to move on. So now what we've done is essentially we've set up our simulation model where we've got a beacon that's projecting a sound wave. We've got a hydrophone array that's listening to the sound wave, and it's able to so we've got the receiver and the transmitter set up, and we see that we're able to pass information back and forth, right? Now comes the fun part. Now that we've established that we've set up a simulation model for this. Let's try and use one of our direction of arrival algorithms to actually find what direction is the sound source coming from, right? So what we're going to use here is we're going to use this music estimator. So if we open up the doc page real quick and I show you what, let me look at. So as you can see, this is in our doc page. We've got a number of DOA algorithms, so beam scan estimators, and again these are based on specific geometries. But you've got you've got the beam scan algorithm for a ULA. You've got root music estimator, the music estimator, the MVDRE. These are all very common direction of arrival algorithms, right? So we've implemented them all for you. You don't have to go ahead and waste a lot of time trying to write the code for this. It's all there. You just need to pick it and use it. And the good thing about this is once you set up your simulation environment, essentially you write another line of code here, and based on that data, it'll tell you which algorithm works best for you, right? Okay, so what we're using is the music estimator here. So it's a very popular algorithm. We feed in the sensor array. So these are some of the properties that we have to feed in. The sensor array, the propagation speed, the operating frequency, scan angle. So what are you expecting your array to scan at? So we're saying, okay, -90 to +90 in increments of 0.1. You want to set this DOA output port to true because this is what will output the actual DOA value, the angle from which the signal source is coming from, and then yeah. So now that we've set up the algorithm, right? All of these algorithms have similar properties. You just feed in a lot of the same values. What we're going to do now is we're going to collect 500 pings. Okay, so what we did earlier was we only got 10 pings because we wanted to see what the signal looked like, right? So now we're going to run that same loop 500 times. And essentially what we're going to do is use this algorithm to compute what direction the sound wave is coming from, right? So we've got this for loop here. Again, we set it to 500. Okay, we're doing the same thing that we did earlier, where we use the beacon platform and the array platform and compute its position and velocity at every sample time. Same the isopaths function again very similar to what we did earlier, where we're finding the path matrix. I believe this is the Doppler effect, if I'm not mistaken. Any losses that you have in the signal, things like absorption losses when the sound waves hit one of the interfaces, there's some losses that happen out there in the signal, as well as the receiver angle and the source angle, right? This is what comes out of that isopaths function. So we're computing all of that, doing the same thing with the generating our transmitted signal and our receiver signal, and then using that array collector to collect the signal. But then this is where we boost that signal again because we're using that preamp, and then this is where we pass the signal into the algorithm that we created. So you see this music spatial spectrum. This is the system object that's used to create this the system object that implements that algorithm. And all that we're doing here is we're passing the signal, the received signal into this the system object, which is going to give us the angle at the end, right? So let's go ahead and run this real quick. Hopefully it doesn't take too long to run. It's a little slower because I'm sharing over Zoom, and so there's like there's obviously some losses. Okay, so it ran pretty quickly. And now we can plot it, right? So we can plot it in, it's gonna take a second. I don't know why these plots are acting up. But I ran this earlier, so this is what the plot looks like. I don't know why it's I think this it's got something to do with some graphics, something somewhere. But essentially what happens is the red line that you see that's kind of straight and not noisy, that's the actual direction of arrival, or that's as and the reason why it's increasing is because you know that the beacon is stationary and our robot's kind of moving, right? So the angle is going to change at every pulse instant. But what the blue sort of squiggly noisy line is, that's the actual direction of arrival that the algorithms computed at every pulse. So the loss is actually not terrible. You know, it's I think it's less than 1 degree away from what the actual angle is. So you know, just this the canned algorithm out of the box is actually pretty accurate on its own. There are some, I was playing around with this last night, and there are some fun things you can do. Like you can, for example, if you go ahead and change this velocity, right, and you sort of bump, you say, okay, I want my I want my robot to be moving at, say, 5 meters per second, which is kind of fast. And if you run this whole thing, you'll see that the algorithm actually performs pretty badly. Hopefully it'll plot. But yeah, you can see when it moves a lot faster, there's a lot more. I wonder if I can pop this out and scroll in. But as the algorithm gets, as you try and move it quicker, you see that there's a lot more variance in the value here. But at the same time, if you and see so this is that signal I was telling you about. You know, the 10 signals plotted one over the other. I'm going to go and change this real quick, and we can play around with the simulation. So this is really the power of simulation, because you can now play around with these values and see what works best. So let's flip them around and let's see. Okay, let's keep the array platform let's keep the array stationary and move the beacon. Let's see what happens in that case, right? So if we flip these around and run it, we should expect our angle to sort of be in the other direction, right? Because now the relative motion is different. And so yeah, so this is essentially a nice little simulation environment that you've got set up. You can try out different algorithms. The good thing with these algorithms is they all generate code. So whenever you're ready to actually deploy this onto your robot, you can I can open up the doc page for this real quick, but you'll see that you can generate C++ code from this, and essentially deploy that onto your robot, right? Whether you're doing it as a ROS node or as something else, but yeah, it's got the ability to generate C and C++ code, so you can deploy this as a ROS node into your ROS network without MATLAB being in the loop at all. So it's significantly it runs, the performance is a lot better than just running it in MATLAB, because it's actual low level C code. But yeah, real quick and simple. This is how you'd set up a simulation environment for your direction of arrival. This is all a part of the phased array toolbox, so you guys should go check it out. And then if you'll have any questions, please reach out to us. Where you can reach out to us at roboticsarena@mathworks.com. It's a good email, or we've got a page where you can go and request software from. Let me pop that in the chat real quick. but if you go to that page, you should see a request software button, which once you get the software, you have access to the phase array toolbox as well, which will give you this example, and yeah, you can try it out. And if you have any questions and you need any help, please feel free to reach out to us at any point in time. So that's all that I have today. We can hang around a little bit for any questions from the people on the call, but if not, you need some help, we're here to help you. So please reach out.
We do have a question on social media. So it's
Oh,
from one
yeah,
of our
absolutely.
folks that's with CPerch. So they have some of their students are interested in tech careers, and they would love your thoughts on what the best pathway through education is for a career at a company like MathWorks.
So the MathWorks is very unique because we're technically a software company, but our tools are used by a lot of non-software engineers. So our tools are used by mechanical engineers, electrical engineers, engineers and scientists in general. We don't particularly make tools for other software programmers. We make tools for engineers and scientists. So a lot of people that actually work at the MathWorks are, have varied engineering backgrounds. Like I think one of the requirements for us to, if you look at any of our jobs postings, they're not, unless it's a specific software developer role. The general qualification is you need to have some degree in engineering, right? So it could be any kind of engineering, as long as it's because we have products that sort of cater to people in a wide variety of engineering. So yeah, I think the learning path is you probably want to go to school and get an engineering degree, and that opens up a number of options for you. We have, I'd say, the significant majority of people at the MathWorks have master's degrees, just because of the specialty nature of the products that we make. So very often, I'm a mechanical engineer myself. A lot of people on my team are not programmers because we're all end users of the product. Like we've used a lot of MATLAB in school, and some of us if we've had jobs before, we've used MathWorks products there as well. But yeah, the path in is definitely, at least if you want to work on the tech side, you want to get a degree in engineering, in some kind of engineering, right? The more popular ones that we have here are mechanical engineers or electrical engineers. Yeah, and as Scott mentioned in the chat, all STEM majors code. Like that's, yeah, it was funny growing up. The reason I became a mechanical engineer was because I did not want to code, and now I work at a software company. So that if that doesn't explain everything, that's, yeah, you need to know how to code if you want to get into STEM. That's just the way it is. So pick up a language. MATLAB's really easy to learn. Python's easy to learn. The good thing on MATLAB is MATLAB has a lot of very good documentation. So like literally, I can show this to you real quick as soon as I can find my mouse. But this is our doc page. So if you go to our documentation home, literally you pick any product you want. You pick MATLAB. There's a getting started section. You can go and look at, you click on the functions tab. This is literally every function in MATLAB that has a doc page with it that tells you what it does. It shows you how it's used. And then it also tells you okay, these are some topics, or you can, once you're on this function, you click on an example and it'll show you, okay, these are some of the examples in our toolboxes that use that particular function. So every function that we have is documented, which is not always the case with other products or with other softwares, especially Python, because Python is open source. Just the nature of it, people tend to write functions and put it up on the internet, and there's not a lot of documentation. Sometimes you're kind of working with black boxes. You don't know what you're doing, but everything that we have is documented. Okay, I have a question, one more question. We plan to use a microphone array in air to detect distance and bearing to another vessel using a typhoon. This is so, Otter, I'm sorry, I'm not a signal processing expert or an expert on face-to-face communication. I could recommend you talk to if y'all can reach out to the people from Emory Riddle, they have a lot of experience with this kind of stuff. There was a PhD student that used to work on the robotics teams. His name was Stephen Cronin. He did a video with me a few years ago on this topic, but that was what his PhD research was in. So I'd recommend reaching out to him, because I'm not really an expert in this. I haven't really worked on these kind of problems, so I wouldn't be able to give you the right answer. But I know that Stephen will have an answer for you. And I'm sure if you reach out to if you reach out to the Embry-Riddle robotics team, they'll connect you with him, because I'm pretty sure he's still pretty involved with that team. So hopefully, I'm sorry I don't have a better answer for you, but hopefully that helps. Alrighty. Do you have any more questions in the chat? I don't know if y'all can. I mean, if you want to, y'all can turn on your microphone and just ask. I don't need to put it in the chat. We're like 5 of us in this room, so.
Scott asked, he missed the beginning of this, and he was wondering if there was a link for the acoustic simulation problem setup.
Yes, I pointed that earlier in the chat.
Let me find it, and I can.
I'm just going to ping it again.
Thank you.
Into the chat, so everyone's got it. Oh, and then I can also show you what the so this is the one with the passive sonar system, but there's also like this example. So underwater target detection with an active sonar. This is again this application. So this sort of shows you what the paths are and all that kind of fun stuff. But it does something very similar. It just sets up an active sonar system as opposed to a passive sonar system. So this is what the array geometry looks like. The azimuth cut of the array. Yeah, so it's this toolbox is really cool, especially if you're doing anything sort of audio sonar related. There's a whole section on beamforming and direction of arrival. So again, you've got it with a microphone array. There are a whole host of examples that you can take a look at. So beam scan, these are like a few of the different algorithms. I don't believe it uses a hydrophone. I think these are just microphones. But I mean, you just change the array, right? You change it from a hydrophone to a microphone, or a microphone to a hydrophone, and you're good to go. There are also Simulink examples. So this is a Simulink based example. If that's something that you'll want to use. I personally, I'm a huge fan of Simulink. I think Simulink, it's such a great tool that it does not get as much love as it should, especially in the education community. But Simulink is a great tool. I don't like writing code. I like dragging and dropping and connecting boxes, and Simulink allows me to do that. So, that's another option that you can go and check out when you have the time. All right. Maybe hang on for a couple more minutes if there are any questions. If not, I'm going to ping our email address into the chat that you can reach out to us. We have a whole bunch of engineers here that will reply, or depending on who's in that day, we'll get back to you if you have a question. But make full use of the software offer. You get a lot of products with that. A lot of the things that you're trying to do with RoboNation have already been done. If you look enough in the documentation, you'll find solutions to most of your problems in there. And if you don't, well, just reach out to us and we can try and help.
Can you hear me?
Yes.
You mentioned earlier you can generate your MATLAB code onto C. Is it possible to do that to Python?
I don't know why you'd want to convert it to Python, because the advantage of MATLAB and Python are both high-level languages, right? There is an interpreter that's the reason why you want to generate C++ code from MATLAB is because you want to run it on hardware, right? So hardware, we have this product called, let me actually send you, we made a training on this. which will give you an idea as to why we do this. But the idea is that when you're trying to run code on hardware, you want to have absolute low level, C, C++ code running on the hardware, and that's why you'd convert it into C, C++. With Python, it's more they're both high level languages, so you're not going to get any benefit from doing that. But let me send you to that training resource real quick. The one thing that you can do now is you can actually call. So it works both ways now. You can call Python libraries from MATLAB and MATLAB libraries from Python. So if you've got other code that's in Python, but you want to use this particular algorithm, there are ways that you can essentially fire up a MATLAB kernel either in a Python environment or the other way around. So you can sort of get the best of both worlds, right? Student competition. There we go. So this page that I'm popping into the chat is essentially got a whole bunch of like resources for students. Particularly if you look at the MATLAB and Simulink robotics arena, that's got a bunch of videos on things like ROS. I think there's a video on direction of arrival estimation in there. Perceptions, if you're trying to do deep learning and some of that kind of fun stuff. There's a bunch of videos on that. But if you scroll down to the code generation piece, that is what talks about converting MATLAB or Simulink code into C, C++. And for that training, we use an Arduino and we use a Raspberry Pi. So Arduinos are great for like motor control. If you design a PID controller, you simulate it in Simulink. You essentially hit a button, it'll convert the whole thing into C++ and deploy it, and you don't have to touch the low-level code at all. So what that allows you to do is whenever you're programming or you're spending time programming, you're doing it in a high-level language, which is easier. It saves you a lot of time with dealing with bugs and things like that. But then as long as your MATLAB code works, your Simulink code works, we sort of give you the guarantee that once you generate C, C++ out of it, it'll perform in the same way. It's a very popular workflow used in industry. In fact, most of the cars you drive is essentially running code that was generated from Simulink or MATLAB and deployed onto, because we've got a product called Embedded Coder. And the whole thing with Embedded Coder is it tries to optimize the code. So it's smart enough to figure out, okay, if you've got like parts of your code that are kind of dead and not doing anything, it's just going to add useless memory to your typically an embedded controller is small. You want to save as much, you want to be as efficient as possible when you're deploying it to an embedded controller. So it's smart enough to figure out, okay, certain pieces of your code are not really doing anything, or we can shrink that portion of the code, but and deploy it. But at the same time, you can also take a look at it and edit it yourself if you want to. So it's not like it's generating C, C++ code that you can't read and can't edit. You can open up the code, read it, make edits. Another very common workflow with that is people will, just as you mentioned, right? Maybe you have one algorithm in MATLAB that you really like and you want to generate code for that one particular algorithm. You could essentially export that algorithm as a DLL or a static library or whatever, and then just integrate it into whatever other code you've got. So those are a couple of different workflows that we have with our Coder products. And I'm happy to talk to you more about it if you would like.
No, I thought that kind of answered my questions.
All right.
Thank you.
Awesome. All righty. Well, if we don't have anything else, I think we can call it a day. Thank you so much, guys, for showing up. Yeah, please, if anything comes up, please reach out, with questions. We're happy to help.
Our next session will be on March 2nd. So we hope you can all join us for that, and we'll send an email about that soon.
Yeah, I believe we're doing path planning over there. So yeah, should be fun. My colleague Jose will join us for that, so it should be a good time.
Thank you guys for coming.